Example 4 tells us that there's a spherical balloon being inflated at a constant rate, where its volume is being inflated at a constant rate, and that rate is 150 cubic centimeters per second, and a cubic centimeter, of course, is the same thing as a milliliter. After t seconds, the radius of the balloon is r cm, and we're asked to find the rate of change of the radius with respect to time when the radius is 50 centimeters. So, how do we do this? We're asked to find dr. We're asked to find dr by dt. What do we already have? We already have the increase in volume with respect to time, which is 150 cubic centimeters a second. So, what are we going to do with this one? How are we going to work this out? Well, I'm probably going to have to use this dv dt at some stage. Now, how would I cancel out this dv? Well, I'd need a dv down here, and I need a dr for this one, right? So I need to find out what is dr dv. Now, this sounds a bit weird, right? Because I don't often consider the radius in terms of volumes. Usually I consider the volume to be equal to pi 4/3 pi r cubed, right, for a sphere. But hold on, I have another formula that I can use, or another trick, and that is dr by dv is going to be 1 over dv by dr. That is, I can just take the reciprocal of this one, and I get this one. So, what do I need to do now? I just need to differentiate this and find the reciprocal. So if I differentiate this, dv by dr is equal to 4 pi r squared. Therefore, dr by dv is going to be 1 over 4 pi r squared. And now I'm more than capable of putting this into my formula, right? So what do I get? I get dr by dt is equal to 1 over 4 pi r squared times 150. And in particular, I'm interested in this when r is equal to 50 centimeters. So dr by dt, when r is equal to 50, I get 150 over 4 pi 50 squared. 50 squared is 2,500 times 4 is 10,000. So this is 150 over 10,000 pi, which is equal to, I believe, 3 over 200 pi cm per second. So this is the first part. The second part, instead of looking at the rate of change of the radius, we want the rate of increase of the surface area of the balloon, and the radius is again 50 centimeters. So, how are we going to do this? This time we're asked to find the rate of change of the surface area, so d of the surface area, with respect to time. Well, again, this is going to be the surface area with respect to the radius, which we can work out fairly simply, and the radius with respect to time, which we already have from the previous part. So, what is the rate of change of the surface area with respect to the radius? Well, we know the surface area for a sphere is 4 pi r squared, so the rate of change of the surface area with respect to the radius is going to be 8 pi r. So, what do I get? That means ds by dt is equal to 8 pi r times the dr by dt. Now, there's a reason I haven't substituted in my value from the previous part, this one. There's a reason I haven't substituted it in yet. It's because this value is only for r is equal to 50. So, I actually have to come back here and write ds by dt at r equals to 50 before I can substitute this in. So this is 80, sorry, not 80, what am I talking about? This is 8 pi 50 times, and now I put in this value, 3 over 200 pi. So what's that going to be equal to? Well, my pi's are going to cancel each other out. 8 times 50 is 400, I believe, and 400 times 3 is 1200. So I get 1200 over 200 now that the pi's have cancelled, and this is equal to 6. But we can't forget our units. We're talking about surface area with respect to time, so this is 6 square centimeters per second. And that finishes example 4.